Uh, or can you hear us?
Yeah.
Okay.
Yeah.
We're good to go. Floor is yours.
Okay. Okay. So thanks and hi everyone. My apologies for not being able to attend the event. My name is Oren. Today I'll present our paper, how optimal greedy decoding is for extractive question answering. This is a collaboration with my colleagues at the time from Tel Aviv University, Ori Ram, Aviai Frat, and Omer Levi. So first, let's define the task at hand. It's a well-known one. Extractive question answering is where one is given with an informative passage and a question, and the task is to predict the answer to the question, which should be a span contained in the passage. Typically, models are adapted to the task using span selection layer, where a task-specific layer is added to the language model during fine-tuning. This approach emits scores for the start and end positions of the answer from the passage tokens. This method promises two properties. First, it is extractive. This means that the answer is a span from the text itself. It is naturally guaranteed since we select start and end tokens. It is also exact. Since we get score for each possible first and last token pairs, we can select the highest ranked span out of all the spans in the passage, meaning it's exact in its nature. Another approach, alongside layer selection, span selection layer, is to form the problem as a text-to-text task, and then generate the answer using a decoding algorithm over some generative model. Often some naive decoding is used, maybe simple greedy decoding or beam search. One major advantage of this approach is the fact that no new parameters are introduced into the pre-trained model, meaning we can use it in a zero-shot setup. On the other hand, these naive decoding do not promise extractiveness, since the generative model is free to generate any series of tokens. It is not limited to the passage tokens. It is also not exact due to its naive nature. It does not cover all the possible spans in the passage. So our main motivation is finding out under which conditions greedy decoding violates these two properties of exact and extract. And if and when it violates them, does it hurt the performance? And does fine-tuning the generative model on the task surfaces these properties? And how many examples are required to do so? We try to answer this question using a novel decoding algorithm to our knowledge, which we named exact extract. It can be used with generative models for the task, and it is guaranteed to be both exact and extractive. Our main results show that in zero-shot setup, enforcing the two properties of exact and extract using our decoding algorithm shows better results compared to greedy decoding, that's the red versus green. When fine-tuning on a handful of 16 examples, the F1 score gap is drastically narrowed down. And these two properties of exact and extract also improve as well. We measure them for greedy decoding, and we'll see that soon. Now, let's briefly see how our algorithm implements these two properties. As usual, we train the model by feeding the encoder with a prompted passage and a question and a masked answer, and we train the model to predict the answer appended with an EOS token. So first, let's talk about a naive algorithm for measuring all the spans in the text. How can we calculate the probability of a specific span? Well, we use the encoder and decoder. We feed the encoder with the prompted passage and question and a masked answer. The encoder output is then fed into the decoder, which is also fed with the tokenized version of the span we want to get probabilities for. The decoder emits logit metrics consisting of various condition log probabilities, and then we can extract valuable log probabilities from it. We can get the log probability for Normandy being the first word, and that of a condition that follows Normandy, and so on for every token in the passage, condition that follows previous ones. Note that logit metrics also holds the log probability for EOS token, condition that follows any series of tokens we gave the decoder. In this instance, the series of all span tokens. Since these are condition log probabilities, we just sum all of them, and we get the log probability for the whole span being the answer. So naive algorithm would calculate the probability for every span separately. There are n squared spans. Each requires an order of n in space, meaning in total, a naive algorithm would get a space complexity of n to the third. Our algorithm, exact extract, is simply a takeoff on the naive algorithm. First, we know that given the passage, there are multiple spans in it. Take these three, for example. For each, we would like to calculate the probability of it being the answer. Now, know that each span is, in practice, a prefix of some suffix of the passage. That's a suffix, that's a suffix, and that's a suffix too. So exact algorithm simply calculates the probability of every suffix of the passage being an answer, and in the process gets the probability of each of its prefixes with no added space complexity. So going back to the logit matrix, we feed the decoder with some suffix, and we get the log probabilities of every token and it conditioned on its preceding tokens. From the logit metric, we also get the probability of the ES tokens as well, conditioned on every series of tokens from the suffix. Now we can calculate log probabilities of every suffix in the input prefix. We simply sum the relevant condition log probabilities in yellow to get the probability of every prefix in the suffix. So in a single forward pass of the passage suffix through the decoder, which is order of n in space, gives the probability to all its suffixes. And since we have n suffixes, we get order of n squared in terms of space, which is an improvement compared to the naive algorithm. In our experiments, we use T5 large, the vanilla one, published with the original paper, both for zero shot, and we also tested it with a few shot QA dataset presented in the Splinter paper by Ori and Omer and some other friends. We then decode answers using both greedy decoding and exact extract and compare the results to compare both F1 results and exactness and extractiveness of the greedy decoding. First, let's see how good is greedy decoding compared to exact extract in zero shot and few shot settings. These are the results for squad we've seen earlier. And we see that while exact extract in red get almost 10 more F1 points over greedy decoding for a zero shot setup, we see that merely 16 examples, this gap shrinks down to 1 point. And with more training examples available, the gap vanishes up until 1,000 examples, where greedy and exact gets the exact same score. We see the same pattern with more data sets. Even if the gap does not vanish as quickly, eventually, in most cases, it does. So now that we've seen that in terms of performance, exact has an advantage over greedy, mainly in zero shot, we test how exact and extract greedy decoding is in practice, meaning how often it violates these two properties. Extractiveness is simply measured by checking if the generated answer is contained in the passage. It's an obvious one. And exactness is measured by comparing the generated answer by greedy with the answer selected by exact extract, which guarantees it is the most likely span according to the model. So that's how we measure exactness. Let's focus on extractness first. Comparing zero shot with only 16 examples, we see a large gap in extractness performance. And it continues to improve as we add more examples, but not in the same rate as we move from 0 to 16. So the model kind of catches up the extractness task quite quickly and easily. Exactness also behaves pretty much the same with a gap of 30 up to 50 points when moving from zero shot to 16 examples, meaning greedy is eventually selecting the correct tokens as if it is in all the possible spans. So we've seen the main advantage of exact extract over greedy is in zero shot in terms of F1 score, but can we make greedy perform as good as exact extract even in zero shot setup? In that case, we don't need to use the exact extract algorithm. We use RSS pre-training scheme, which was introduced in Splinter paper. In this scheme, basically the model is trained with passages that has recurrent spans in them, and several of them. And during pre-training, a single occurrence of each span is hidden from the model, and it is trained to predict the hidden span. Implicitly, this can be seen as training the model to extract some span from the context. So, and Splinter paper showed this on encoder-only model, and here we use it for a generative model. And using the same, using T5 model pre-trained on RSS and the standard T5, we found that RSS pre-training increases the model performance, both in terms of F1 and extractness, for zero shot. For instance, here for Squad, we get 71 F1 points in a zero shot setup, meaning this model was never fine-tuned for the task. We see a 20 points gap compared to T5 with the vanilla T5 doing 3D decoding. And we also noticed that once we add just a bit of fine-tuning, this gap vanishes quickly, meaning all the advantage of RSS is being taken away by just few training examples. And we see pretty much the same pattern for extractness as well, where the gap drops from 30%, meaning it's 2 times more extractive, to just a few points up until almost none. As for error analysis, we've looked into 2 errors being done by the algorithms, times when greedy was correct and exact extract wasn't, and vice versa. We tried to characterize the cases where greedy decoding is correct, while extract exact isn't, and we noticed a tokenization caveat. There are samples in the dataset where the annotated answer in its tokenized form does not appear in the tokenized form of the context. For instance, here 2000 as a single token, and here 2000 surrounded by parentheses. We've separated the text set into samples where the tokenized version of the annotated answer is contained in the tokenized context, that's S in, and its complementary set, that's S out. In parentheses here, percentage, you see how much of the whole test set each group is, the size of it. It is easy to see that when the answer is cannot be extracted as is in its tokenized form from the context, the exact extract fails much more than in the other set where it can be extracted. So that's one problem that makes exact extract fails more often than not. As for the other case, where exact extract is correct, but greedy fails, and this is in my perspective, the interesting case, because greedy is so commonly used, we did some sampling where we took samples where greedy was wrong and exact extract was right, meaning the model could have chosen the correct span, and we manually classified them into several groups. So in half of the cases, the answer was just incorrect. And the other half of the cases, the answer was correct. But we saw some interesting cases there. In 17% of the times, it was actually extractive, and the answer was correct. It was merely an annotation mistake. The annotator just did not choose one legitimate span that the model did choose. So this is can be regarded as a false negative. In the other cases, in 30% of the cases, it was not extractive at all. But sometimes it was semantically correct. In 23% of the times, it was a paraphrase, meaning the answer was pretty much the same as it appears in the text, but the selected tokens were a bit different. Here you see an example where it was chosen to express numbers in words rather than digits. And in 7% of the times, there was just added factual information, meaning the answer was not incorrect, it was completely fine. It had just added information that was probably encoded into the model during pre-training, thus making it not extractive by definition. So to summarize, we came to the conclusion that greedy decoding scarcely violates the exact extract properties with just a handful of training examples. Its performance doesn't get a hit. And this violation, mainly in zero shot, can be mitigated with RSS pre-training alongside some improvement in performance. And the violations sometimes just stem from annotation issues that we've just now seen and tokenization limitations, which probably varies across models. Thank you, that's all.
Okay, so we have a few minutes for questions. Anybody in the room with a question? Otherwise, there is one online question about why this is considered extractive QA then rather than abstractive. But yeah, or
well, the task itself is by definition extractive, and that's what the model was measured for. If we're talking about abstractive QA, then the measurement of extractiveness won't be as interesting. And in a practitioner point of view, extractive sometimes is a property one would like to maintain.
got it. Thank you. And just for information, this was a question about an earlier part of the talk. I think it was a bit out of context. But so one more question for me. Have you considered constraint decoding, like having a prefix tree or something like that, that you use while doing decoding, and how would that fare in this setting?
Well, you could do that, and then you would probably get pretty much the same results. You would just use another algorithm to force the model to be the decoding to be extractive, if that's what you mean by enforcement. And you would get the same results, but it would be not as efficient because you couldn't probably do that in batches. We try to play around with it a bit, just in terms of the metrics manipulations. Not all can be done in parallel when doing constraints.
Okay, yeah, you should talk to Nicola, actually, but if you were here, but you should still do it. So I think we should move on to Tom's talk. Thanks so much again to all for a great talk.
Thanks, everyone.
Thank you.